We have these different carbon reservoirs as part of the carbon cycle, the atmosphere, the land, the ocean, and then fossil fuels. So these are units, the same units as Ralph used. I'm calling them gigatons, which is billion metric tons, but it's the same, you know, he said billion metric tons, so it's the same thing. And the human perturbation to that is to take carbon from the fossil fuel reservoir and put it in the atmosphere, and also to take carbon from land by cutting down trees for agriculture and put it in the atmosphere. So we have these perturbation fluxes of carbon every year going into the atmosphere. And then the atmosphere, as Ralph showed you, is not rising as fast as it would if this was the only thing that was happening. What's happening is that the carbon cycle is responding to our perturbation by enhancing uptake of carbon from the atmosphere into the land with some non-negligible rate, and also by dissolving in the oceans at a significant rate. So to start with the land uptake first, I think the carbon cycle and paleoclimate is telling us that ultimately the land is not going to keep helping us out here. That's where we're going. One reason I say that is because most of the carbon on land is stored in soils, as Ralph showed. And this is a map of soil carbon concentration. And what you see is that all of the red colors are in the high latitudes. This is because when it's cold, the carbon, you know, the dead leaves and things like that break down very slowly. It's like a ham sandwich in your refrigerator. It lasts longer than if you have it out in the hot sun in the window or whatever. So if we turn the planet into a tropical paradise, we expect to have less carbon in these soils. Another reason to think that land could start decreasing its carbon uptake comes from studies of carbon in forests. So this is from a study of 2 different forests in Europe, one in France and one in Italy. And you have the black line is the carbon uptake in the year 2002, which is sort of a control year. And then in 2003, they had this massive heat wave, which cut the rate of carbon uptake by 50% in both cases. So the carbon cycle can respond quickly to changes in climate as well. I mean, this is just a stressful situation for the poor forests. And then thirdly is that the reason that Ralph already pointed out, ultimately the land is going to be swamped by fossil fuels if we go there. There's, you know, roughly 2,000 gigatons in the land, 5,000 gigatons in the fossil fuels, and so, you know, if we put all of this into there, the land is going to run out of capability to help us out. With respect to the ocean, the way that carbon is stored in the ocean depends very strongly on this chemistry of the carbonate buffer system, it's called. CO2 reacts with carbonate ion to make a bicarbonate ion. So this is the same chemistry that we have in our blood. We breathe in oxygen, we breathe out CO2. For oxygen, it doesn't have any of this sort of chemistry. There's no buffer, there's no companions for it to run around with. And so for oxygen, biological beings had to invent hemoglobin to carry oxygen from our lungs, you know, to our cells. But CO2, we don't have to worry about hemoglobin because we have this buffer system. The ocean has the same thing, and as a result of this buffer system, the ocean stores a lot of carbon. 38,000 gigatons of carbon in the ocean is because of this buffer system. So the amount of carbon that the buffer can hold depends on the amount of carbonate ion, the CO3 that's there for the CO2 to react with. As the CO2 concentration goes up, that changes the chemistry of the water. This is called ocean acidification. CO2 is an acid. If you acidify the water, that means you decrease the amount of this carbonate ion that's available for the CO2 to react with. And so the ability of seawater to hold more CO2 gets weaker as this buffer gets used up. It's a finite capacity of the seawater to hold carbon dioxide. Then there are also recent studies that seem to suggest that the uptake of CO2 into the oceans may be slowing even more than the acidification wiping out the buffer system would suggest. So if the ocean circulation and biology were staying the same, we would expect the uptake of CO2 into the Southern Ocean to follow this red curve here. So here is 0, and if the number is less than 0, that means in this figure that CO2 is going from the air into the ocean. And the Southern Ocean is an important place for getting CO2 into the ocean because that's where the deep ocean is in contact with the atmosphere. That's how you get CO2 from the surface into the deep ocean, which is where you want it to go. So this is what we would expect is for the CO2 invasion into the ocean to increase because there's more CO2 in the air. So you put more in the air, more will dissolve in the water, and you can kind of shove it in there faster, which is what seems like it's mostly happening according to the data that Ralph showed. But what they observed based on looking at the concentrations of CO2 in air around the world, they try to figure out how much, okay, so the air is blowing over the ocean, and you measure the CO2 here, and you measure the CO2 there, and if there's less CO2 after it gets to the other side than you started with, then you assume it's going into the ocean. That's kind of the idea of this sort of study. And what they found was that the rate of CO2 going into the ocean has been sort of flat since sort of the 80s, rather than increasing the way we would expect because of the higher CO2 concentrations. There's a similar sort of study for the North Atlantic, which found changes in the circulation of the ocean apparently, which is also what's going on here, apparently are impeding the CO2 invading into the ocean. So if you warm the surface or if you make it fresher by changing the rate of rainfall, you make the ocean stagnate, and if you're not making water go down into the deep as quick, then maybe you're not letting CO2 go into the deep ocean as quickly either. A third thing that I can bring to the table with respect to these carbon sinks comes from the behavior of CO2 in the natural climate cycles in the past. So this is the CO2 record from the Vostok ice core and the temperature record going back also. So you see lower CO2 in glacial times when it's colder, and then higher CO2 in interglacial. So the CO2 today actually is up right around 380 or something. That's not on this plot. But there's this sort of loop of cause and effect between global temperature and CO2 on these time scales. The way that the system seems to be working is that the progression of climate between glacial and interglacial is paced or originally prodded by variations in Earth's orbit around the sun.